All right, here we go. Come on. There we go. Whoa. All right, you ready for some cool stuff? All right, a lot of the things that I am going to show you in this class, like animations, I usually code those up myself. This one I did not do. Okay, so I don't want to take credit for this. Everything else that I've shown you that's an animation or anything, unless I state otherwise, I've done it myself. The code for this, it's not complicated, but it's just that it's already been done. So I didn't want to have to rewrite this. They did it really nice, so I'm just using it. So check this out. Let's say we have two curves, right? One thing I don't like about it is we can't take these curves off. I have to leave them up here. So we have two curves there, right? We could find the area between those, theoretically. Those are functions of x. Whoa. Oh, I know what's going on here. Right, those are functions of x. These are functions of x. They pass the vertical line test. So we could find the area by just doing a rectangle like that and then moving our rectangle from left to right. Right? Okay, no big deal. Area. That's not what we're interested in now. We're moving into 7.2. In 7.2, the title of the section is volumes. Volumes. Now, volumes, for the volume, to measure a volume, you need three-dimensional space, don't you? Area is two-dimensional. Length is one-dimensional. Volume is three-dimensional. So what I'd like for us to do is imagine, let me take that area out of there. Imagine if you could, see if you can imagine this. Taking the area between these curves, all right? And let's just take this whole graph and just kind of move it out into three-dimensional space, all right? And take that area between those two curves and just rotate it around the x-axis and just bring it all the way back around to where it meets up at the top again. And you would have this solid shape. Y'all see it?
Yeah, some weird.
And there'd be clear space in the middle?
And there would be some space in the middle, right? Yeah, but this is 2018, right? We have technology. So let me illustrate it with this. Okay, so imagine this is now like three-dimensional. Do y'all see that? Right? Y'all are amazed too easily, right? And here's that area that we're about to rotate around the x-axis. Now, I believe they're calling it the t-axis, but this is the x-axis for us, okay? So here I go, all right? Here it comes. Let me start rotating this. Okay, here it goes. I'm going to rotate around all the way to the other side. There we go. Y'all see that? Now, obviously this solid has volume to it. Agreed? And we want to know what that volume is. But there's some weird stuff happening. I mean, obviously the outside is kind of strange, right? Because it's shaped by that outside, isn't that shaped by that top function? The inside is actually shaped by the bottom function. Because if I make this somewhat semi-transparent, you can see that inner hole is not straight, right? It's not just like you drilled through. It's got some weird undulations in it, doesn't it? And we would like to know what the volume of that is.
So volume between them?
The volume, yeah. So if this were some sort of container, how much stuff is in it, right? Yeah. You'd have to, take out the fact that that part's empty, right? So how much stuff is there? Does that seem like a reasonably difficult problem? I mean, it appears like that would be tough, right? To do? No? It seems easy? All right, so let's see. How are we going to do it? How are we going to do that? And this is the beauty of the Riemann sum. This is the beauty of understanding formulas, how to come up with formulas. So we're going to create the formula ourselves right now. All right, here we go. Let's take some function f on top and some function g on the bottom. Let's look at these between a and b. And imagine rotating them around, all right? Rotating that thing around the x-axis. So when we do that, we normally draw this little like double arrow that's curved to let everyone know we're about to wrap this around the x-axis. Can you kind of tell from that picture? All right, so I'm about to wrap that around the x-axis and see what the volume is. How in the world are we going to get a formula for that? Well, let's stick with what we know. What if I were to take an infinitesimal rectangle here? Well, that rectangle doesn't tell me anything about volume, right? It just tells me about the area. But let's move over here to the side like we did before. Let's take that little rectangle up here. Let's remember that the top function there is f and the bottom function there is g, right? Whatever they're doing, that's what's dictating that rectangle's height. Agree? Nothing new here. Now, if I tell you to take that little sliver and wrap it around the x-axis, what would it look like to you? A washer. So think about a bolt, right? A washer. So I'm actually going to wrap this around. So I'm going to do a third picture now. So see if you agree with me that that would look like this infinitesimally thin sliced washer. Do y'all see that? You sure?
Yeah.
Okay. So that's like the little rectangle was in here, but it got wrapped around, and so it created this washer. Does that washer have a volume? It does. If we could come up with a formula for the volume of this single washer, then all I'd have to do is add those all up, right? Remember we came up with the formula for the area of one little sliver, and then we added them up with the integral? If I could come up with the formula for the volume of this single washer, then I could add them all up and get the total volume of the entire thing. Because all we're doing to create the volume of the entire thing is taking all of these little rectangles and wrapping them around and creating a bunch of like infinitesimally thin washers, right? Y'all see that? Okay, so let's see if we can't figure out what the volume of this is. All right. Would you agree with this? Draw this again. The washer with the hole in it is equal to the washer without a hole in it minus that small hole. Yeah? I mean, is that obvious to you? So the volume of this is equal to the volume of that minus the volume of that. Agreed? Okay. One more thing I need to remind you of. Back in pre-cal, or some class way before this one, if you have a cylinder, a right cylinder, which means it's a right angle, okay, right-angled cylinder. If you have a right cylinder, what's the volume of a right cylinder? So this is a formula. Pi r squared times the height. That's the volume of a right cylinder. So we need to label some things here. The height of the cylinder is h, and then the radius of the cylinder is your r. So look at the formula. Do we recognize pi r squared? That's the area of a circle, right? So this is basically saying you take the area of that circle up top and you multiply it times the height, which gives you like the depth, and that gives you the volume. Okay? We have to understand this formula and believe it to be true. Can we take that on faith? That that's true? Okay, so if we want to find the volume of any cylinder, we need to know its height and its radius, don't we? Yes? Okay, so let's go back over here. We want to know the volume of that, right? Which we said is the volume of that minus the volume of that. All right, I'm going to draw that picture again over here. The volume of the one with the circle cut out is equal to the volume of the one without the circle minus the little one. Okay, help me get the volume of these guys. This is equal to, okay, what's the volume of this one? Well, how thick is it? Dx, right? Isn't it dx? The width of this is dx. Why do we know it's dx? Well, that was the width of the rectangle, right? That was the width of the sliver. So we know that this is dx. Now, do you know the radius of this? Do you know the distance from here to here? That's the big one, right? The big one is this one. What's the distance from here to here? That's the f function, isn't it? It's the f function. So that distance right there is the f function. So according to the formula, the volume of that little cylinder, that's a cylinder, right? It's just sideways. It should be pi times what? The radius, which is f. I'm just going to put f squared, right? Times dx. Minus, now, what about this one? So this one here is this smaller one, and that means the radius on it is dictated by g, isn't it? So the radius on this one is g, and the width is still dx, isn't it? So the volume of that little guy is pi times g squared dx, right? Now, what do both of those have in common? They both have a pi and they both have a dx, don't they? So I'm going to factor out a pi, and I'm going to factor out a dx. But notice the way I factored out that dx. Factored the dx out to the right side. I factored the pi out to the front. Now, I did that because this gives us a formula for the volume of one sliver of the entire thing, right? So now I bring in the Riemann sum, the integral. I want to integrate this, right? I want to integrate this formula from where to where? A to B, because we're still going to let this rectangle slide from A to B, right? Which is going to make all these washers appear. So I'm still going to go from A to B, and I'm integrating this formula, right? Pi is a constant. It comes out of the integral completely. And then I have f squared minus g squared dx. Holy crap. That's the formula right there. This is it. If you have two curves where f is greater than g on the interval a, b, so that we still have that formula, right? That condition, we could say equal if we wanted to. So if you have a function that's on top of another function on some interval, and you would like to wrap that around the x-axis and see what the volume of that object would be, then all you have to do is square each function, subtract them, integrate, and then multiply by pi when you're done, right? And that's it. You'll have the volume.
That's for any function you want to wrap it around and get the volume.
Yep.
That's cool.
Okay. So you ready to do something really cool? Yeah, I think we're ready. I'm going to jump into this one. We'll do more examples of this next class, but I think this is probably going to be the most exciting example that I can give you right now. Okay, does anybody know what the volume of a sphere is? If somebody gives you a sphere that's three-dimensional
Isn't that four thirds, 5?
with a radius, right? It's what? 4/3 pi r cubed. Where did you get that from? From memory, right? Someone gave you that formula.
Isn't that from like a...
It's from the formula sheet, right? Now, do you remember a few classes ago we proved that the area of a circle is pi r squared? We're going to prove that the volume of a sphere is 4/3 pi r cubed. We're going to do that right now. I hope. I'm just doing this on a whim, so I'm hoping we can actually do this. So how do we do this? Well, we go back and we can only do volumes right now by wrapping things around the x-axis, right? That's the formula I just gave you. So to create this sphere, you could take like a circle and like wrap it around the x-axis. Does that kind of make sense? So imagine this. Let's say we have a circle, and that circle has a radius of r. That's a terrible circle, but we've already established I can't draw good circles. All right, so there's a circle of radius r, yes? Centered at the origin. What if we just take that first quadrant arc, that arc in the first quadrant, and wrap that around the x-axis? Could we do it? Yeah, we could do that. And if we wrap that around the x-axis, we would get half of that sphere, wouldn't we? So we could double that answer if we could get it, right? So let's see if we can't come up with this right here, what this function is. And we did this before. We said this was x squared plus y squared was r squared. Do you remember that?
Oh.
Remember that?
Yeah.
That was the equation. We did this, right? We proved this. And then I solved that for y, didn't I? Now when I solve that for y, I have to do plus or minus, don't I? But I'm only going to do the plus because that's the top half. The minus is the bottom half. So I want to be able to integrate that, yes? Okay, yes? Are y'all with me? Come on, we're about to show that this is true. It's pretty awesome. I want to make sure y'all are with me. We are there? Okay. So I'm going to wrap that. What is the bottom function? Because I'm supposed to have a top function and a bottom function. Well, it's the x-axis, right? Which is y equals 0, isn't it? So I'm going to be putting rectangles in here. And I'm going to make washers out of these, although it's not going to be a washer because there's no hole in the middle. So it's actually a disk, but who cares? This is my x-axis. Here's my rectangle. What's the function that's always on top? What's this thing that's always on top? That one right there, right? I'll call that f. F of x equals square root of r squared minus x squared, yeah? What is the function that's on the bottom? G of x equals 0, right? It's just the flat line. Okay, according to the formula we just created, the volume we would get from wrapping that around the x-axis is pi integral from where to where? And we never established this, but we're going to start at 0 and stop where? At r, because r is the radius of the circle, yes? Okay, so we're going to go from 0 to r. And what are we integrating? F squared, right? Ah, beautiful. What is this squared? R squared minus x squared minus this squared. 0, right? So that's all we're integrating? Dx. And I really have no issues integrating that. This is going to be pi. Okay, let's get the antiderivative. What's the antiderivative of r squared with respect to x? Remember, r is a constant, right? So r squared x. And then what's the antiderivative of that? 1/3. I had a 3 in here. 1/3, what? X cubed. I had a cubed in here. All right, and I'm going to do this from where to where? 0 to r. All right, let's plug in r first. We plug in r, what do we get? R cubed, sorry, minus, that's a cubed, 1/3 r cubed, right? That's what we get when we plug in r. What happens when we plug in 0 for x? It's all gone, right? So isn't this pi times r cubed minus 1/3 r cubed? That's 2/3 r cubed. That is the volume of half of my sphere, right? Because I only wrapped this around. So the symmetry, if I double that, it gives me the answer, right? So if I multiply this by 2, what do I get? Get that. If you look back on how we showed that the area of a circle was pi r squared, right? If you look back in the notes, it was harder to show that than it was to show this. because on the one where we were showing that the area was pi r squared, we didn't have the luxury of squaring that function. So we had to use trigonometric substitution to do that. But here, because we got to square it, things got nice. Okay? All right, that's pretty awesome. What I'd like for you to do tonight is your 7.1 homework. All right, do your 7.1 homework. And we're going to do more of 7.2. There's a lot we still have to do because, well, we'll just save it for next time. Let's talk about the test. I've got 9 minutes.